Hi there, my name is Jessica Brown. I'm an undergraduate student at Mellon College of Engineering and a member of the RIS 2024 cohort. I'm very excited to be speaking about my work from this summer, um, which involves deep instruction tuning the segment anything foundation model so that it performs better on novel object instances. Um, and we deep instruction tune it on um, unsupervised action object segmentations. And I'm going to talk about kind of the end-to-end pipeline that we developed for doing that. So at a high level, the segmentation model that we developed has following inputs and outputs. RGB image data as inputs and text prompts that our segmentation model then uses to generate a valid segmentation masks. Here's how the two components of our method come together. So the inputs to our unsupervised segmentation method are video demonstrations. And then we take the unsupervised segmentations derived from the video, and we use that to deep instruction tune the model, which is segment anything. And during inference, we provide a text prompt and an image, an inference image, and then the output is a valid segmentation mask. Here's how we create the unsupervised segmentations. First, we gather the frames from video demonstrations. And after doing that, we perform what we call keyframe discovery, where keyframes are whenever the robot's gripper opens or closes. So whenever the gripper state changes, or whenever the robot's velocity is approaching zero. We have that ground truth information in simulation, so we leverage it. However, for human video demonstrations, we have a fixed frame gap between keyframes, which is 60 frames. And we assume a 30 frames per second frame rate from the human demonstration videos. So every 2 seconds is a keyframe in a demo. Then we compute the optical flow between keyframes and perform this flow aggregation technique to reduce the noise, because ultimately how we're driving the flow is from a model called Raft. And sometimes the model can produce imperfect output. And so to account for that and to account for frames that may have worse flow, we do this aggregation, like averaging technique. And how we do that is we take the first keyframe and compute the flow between that first frame, let's say it's K1, and we compute the flow between K1 and K1 plus 1. And then K1 and K1 plus 2. And then K1 and K1 plus 3. And all the way up until we reach K2, which is the next keyframe. And all of those flows that we computed in the middle of K1 and K2 get aggregated together. And also there's some normalization going on in there as well. After we have our aggregate flow magnitudes, which is a matrix of flows magnitudes where each pixel has a corresponding magnitude, we threshold based on the distribution of that flow magnitude data. And we empirically discovered that the object being manipulated will have much higher flows than everything else in the video, because we assume that the action object or the object instance being manipulated is the only thing that should be moving, and other than the robot and the human. And to account for the fact that the robot and the human are also in the video demonstrations, we have pseudo ground truth human segmentations, which we get from grounded SAM, and we have ground truth robot segmentations from RL bench. So that's how we get, that's how we are able to do this thresholding technique. And then after we do thresholding and some additional filtering and post-processing, we get our final ground truth segmentations that we use to deep instruction tune segment anything. This is a larger illustration of that graphic. Here are some qualitative examples of the pseudo ground truth unsupervised segmentations that we use to deep instruction tune segment anything. You can see they're not too loose or too tight necessarily. They're actually pretty spot on. This is an illustration of the text prompt and unsupervised segmentation pairs that we use to deep instruction tune. This is the deep instruction tuning model architecture. The language encoder and the segment anything layers are frozen. This is because fine-tuning a segmentation foundation model directly is like extremely computationally expensive, and most people do not have access to the kind of compute resources that are required to do that. That's one of the other reasons why our method is very useful. It's because you can't just take foundation model weights and fine-tune them directly. You need to tune something else if you would like to leverage their superior segmentation capabilities for cases that are still out of distribution for their data. So yeah, the language encoder and the segment anything layers are frozen, while the projection layer between the language encoder and the SAM layers are burning, and so is the mass decoder. Here are some results and their corresponding text prompts. We have both simulation results here and human segmentations. You can see in the last row that we even performed inference with a different person than was used to generate the pseudo ground truth tuning data. And here are some inference videos after training a segmentation model, or tuning rather. And here's a qualitative ablation study on the tuning to kind of validate that it is important to actually tune the model. And you can see that it is. And that is all that I have to share today. Thank you so much for listening.